So let us recall what we have did in the previous lecture. We have talked regarding the existence of triangles in GMP graph model, where P is the probability which we have taken as D by N, where D is a constant. So the expectation of this GNP graph model with this value of P, we have got that the expectation will be D cube by 6, which is independent of N. And we have come to discussion. After the discussion, we have arrived the conclusion that if the value of D is greater than 1.8, then the probability of having the triangle is equal to 0 is less than 1. So in this case, the triangle with the non-zero probability will be there. If it is less than 1.8, the value of D is less than 1.8, then it is very close to 0. So it is simply, it cannot enough edges so that the graph contains a triangle. So this discussion which we have discussed in the previous lecture, and we have discussed with the first moment and the second moment for the number of triangles as a variable x. Now, in this lecture, we are discussing regarding the phase transition. So many of the property of random graph undergo the structural changes as the edge probability passes some threshold value. Now, if you want to see what you mean by threshold value, you just see the one physical example. Suppose you have boiling water. Suppose you are putting the water on a gas, and at some point of time, the boiling water will be boiled. That means it's starting boiling. So when it will start a boiling, then the when the temperature goes to 100 Celsius. So that is known as a threshold value for boiling of water. So in the same manner, we have a graph in GNP graph model. If I talk about, then when you increase the value of this speed, or I can say a probability, if you change the probability, then some properties of graph will be arrived and some property will goes away. For example, what will be the threshold value for GNP graph model so the graph will be connected? So that is known as a transition. So what value of probability if you fix, after that value of P, the graph will be connected always. Then same question one can ask is, when we will have a giant component, what will be the phase transition under which the graph will have a phase transition, giant component? Or what will be the probability that the isolated vertices will be disappear? That means no isolated vertices are there. Same question one can ask is, what will be the transition or the threshold value for that there is appearance of Hamiltonian circuit, or certain diameter will be there, diameter of a graph will be 2. So all these questions, for example, in the previous case we have seen that the threshold value for having a triangle is d by n. Okay, so in that manner we need to find out what will be the when the phase transition is occur and what was the threshold value for GMP graph model. So appearance of cycle in GNP graph model when P reach to 1 by n. So these are the some examples. Let us take that. Saying in GNP graph model, the appearance of first cycle. So when the cycle will be there, it will, when the value of P is reached to 1 by n, and disappearance of isolated vertices when the value of P, it is log n by n. The most important of these transactions are in emergence of a giant component and connected component of size n, which happen when d equal to 1, which we have seen. Okay, so here there are some probability I'm writing, and what will happen, for example, p equal to 0, then so here is a probability. Here I'm writing the transaction, what type of transaction is occur. So that is isolated vertices will be there. If P is of order 1 by n, then there is a forest of a tree. You know what do you mean? What is the definition of a forest? Or I can say there is no component of size greater than big O of log n. If the value of P is d by n, where d is less than 1, then there are component of size big O of log n. If P equal to d by n and the value of d is 1, then there is a component of size big O of n raised to 2 by 3. In that manner, there are certain probability, for example, for this log n upon n, then it is saying that disappearance of isolated vertices. So if you want that your graph does not contain isolated vertices, then your probability should be this. So now the question is, what is the definition of threshold value? And for this and many other property of random graphs, threshold exists where a transaction occur from not having property to having property. So if the graph is not connected, and then after certain things the graph will be connected, so that is known as not having property and having property. So that property is anything you can start with. And for example, a graph will have Eulerian graph. If it is not Eulerian graph, you start with the graph will not be Eulerian. What value of P you can take, so the graph will be Eulerian. So that is the property the graph will does not have. And then you have to change to the some another transaction. So that property will have, like I have given example of water. So once water start boiling, that is the transition of the boiled water. So from one phase to its change to another phase. Okay, so that is here we are interested to study. And what will be the definition of a threshold? That will discuss here. And what is the definition of phase threshold and phase transition? Okay, so this is, I'm giving you a definition that if there are, if there exists a function Pn such that limit of P1 n upon Pn as n tends to infinity is 0, G and P1 at most surely does not have a property. And when limit of n P2 n upon Pn is infinitive as n tends to infinitive, Gn P2 of n at most surely has property. Whatever we are talking about, the property means it is maybe a tree having the occurrence of first tree, or it is isolated vertices, or this disappearance of isolated vertices, or it has a giant component. Anything, any property we can talk here. So if this Gn1Pn has at most surely does not have that property, and if this situation is occurred, this limit is infinitive and P2 has surely that property is there, then we say that phase transition is occurred. So this is the definition of phase transition. And the value P which we have here, it is known as a threshold value for that property. And Pn of n is the threshold. What does it mean of G and P at most surely does not have the property? Means that the probability that is, it has a prob, it goes to 0, has that property will goes to 0 in the limit as n tends to infinity. So what does it mean that this GNP graph at most surely does not have that property? Means that the probability that is has the property, it goes to 0 in the limit as n goes to infinity. And there is a term called increasing property and decreasing property. What does it mean of increasing property? increasing property, for example, a connectedness is an increasing property, because when you increase the value, then the property it has, at some stage it will be a connected, so that is an increasing property. But there are some property which will have a decreasing property, for example having the isolated vertices. So if you can add up the edges into the graph, then the isolated vertices will be reduced. So that is known as a decreasing property. So there is a two terms will have, it is increasing property and the decreasing property. And one thing we should note here that every increasing property has a threshold. So whenever you have a property which is an increasing property, and that means that it has a threshold. So we should write as a note here that every increasing property has threshold. So whenever you have a increasing property, that will always have a threshold. And this is true not only increasing property of the graph at most surely does not have that property, but increasing property of any combinatorial structure will be there, it is true. Now there is a definition of a sharp threshold. So next definition is a sharp threshold. So if you have for C into Pn, if the value of C is less than 1, the graph at most surely does not have the property. So for this value C into Pn, where the value of C is less than 1, when the graph does not have that property, but C into Pn, if the value of C is greater than 1, then the graph at most surely have that property. Then we can say that this Pn is a sharp threshold. Then Pn is a sharp threshold. For example, existence of a giant component has a sharp threshold as 1 by 2. That is an example. For example, I can say the existence of giant component has sharp threshold is 1 by n. Now, to achieve or to find out this threshold and the sharp threshold, you should understand what is the mean of the first moment method and the second moment method to establish or to discuss further things to having the graph at most surely having that property or not having that property. We should understand what does it mean of a first moment. Okay, so I'm just taking for that one, xn will be the number of occurrence of item in random graph. For example, in the in previous lecture we have discussing about the existence of triangles. So in that also we have used that method where we have taken x is the number of occurrence of triangle in the random graph. So whatever the property you are discussing, for example, if you want to discuss about the isolated vertices, that then this item is the isolated vertices. Suppose you are discussing regarding the disappearance of or having the diameter 2, then this item will be the diameter of that. In that manner, we need to see. Then, if we expected that the value of xn goes to 0 as n tends to infinity, then the graph pick a random, at most surely no occurrence of the item. And this is follows from Markov's inequality. So by Markov's inequality, so can somebody tell me what is the Markov's inequality? It says that the probability of x is greater than or equal to a is less than or equal to 1 by a expectation of x. So if this e of x is tending to 0 as n tends to infinity, then the probability of x having, so I'm just saying if e of x is tends to 0 as n tends to infinity, therefore I can say that probability of x is greater than or equal to 1. That means the number of item is greater than 1 is less than or equal to e of x, and this e of x is tending to 0 as n tends to infinity. What does it mean? That the probability of x is greater than or equal to 1 is 0. The expectation of occurrence of that item is goes to 0, which we conclude from this. Because this will tends to 0, that means this probability will tends to 0. Okay, so that we can say. Therefore, we can say that the probability of xn greater than or equal to 1 is 0 if the expectation of occurrence of an item in a graph goes to 0. So expectation of that item, whatever item it is having the triangle, as I told, that whatever the item you are talking about, that we can say it is goes to zero, and therefore the probability that there are one or more occurrence of the item in randomly selected graph goes to zero. And this situation is known as first moment method. This which we have discussed here, this is known as first moment method. That means we have discussed everything which based on E of x. So that is E of x is known as first moment, and using that Markov's inequality, we conclude that the probability of having that item is goes to zero. Occurrence at the expectation will be goes to zero. In the previous section, we shown that the triangle having a threshold value is Pn will be 1 by n. In the previous lecture, this we have discussed. And if the edge probability is P1, if I consider P1 is big O of, sorry, small o of 1 by n, then the expected number of triangle is goes to zero. And by first moment method, that is this, the graph at most surely has no triangle. However, the probability if I take P2, if it satisfies P2 n upon 1 by n, that we have discussed the definition of threshold that we have here. Pn n upon P1 of n is goes to 0, and P2 of n upon P, if it is infinitive, that we have discussed using in the previous lecture also we have discussed, that is this we are talking about probability of x is equal to 0 is less than that we have discussed using the Chebyshev inequality. The probability having the known triangle is at most this much, and which goes to 0. This later case, what we have called this method, it's called the second moment method, and the first moment method and second moment method are both widely used to discuss this phase transition. When the expected value of xn is the number of occurrence of the item goes to infinity, we cannot conclude the graph pick a random will like to have a copy. And since the item may all appearance of vanishing for small fraction of a graph. So for that we need to understand what does it mean of second moment method. The first moment method we already discussed, that is if you can use this situation, that is probability of x greater than 1 and if e of x is goes to 0 as n tends to infinite and as n goes to infinity, we come to know that the probability of having that item that is greater than 1 is goes to 0. Now let us see what is the second moment method, and that can be concluded from the Chebyshev inequality. So this is the actually theorem we have, and the theorem is known as second moment method. Let Xn be a random graph. Sorry, Xn be a random variable, not a graph, with E of X, the expectation will be greater than 0. If the variance of X is equal to the small o of expectation square X, then X is at most surely greater than 0. Since here expectation is greater than 0, it is given. So we are able to use Chebyshev inequality. If the expectation of X is greater than 0, then we can say that X to be less than or equal to 0, it must differ from the expected value at least by its expected value. That is, I am saying that means the probability of X is less than or equal to 0 is less than or equal to probability of mod of X minus expectation of X is greater than or equal to expectation of X. And we use the Chebyshev inequality. Let us recall what is Chebyshev inequality. Yes, anyone? Anyone remember what is the Chebyshev inequality? It's saying that for X is random variable and C is greater than 0, the probability of mod of X minus expectation of X greater than or equal to C will be less than or equal to variance of X upon C square. So here it is in place of C we have expectation of X, and so this will can say it is a variance of X upon C square, which is expectation square X. And what does it mean of what is a given situation? It is the variance of X is equal to small o of E square X. What does it mean of Fx is equal to small o of Gx? The meaning is limit of Fx upon Gx is 0 as x tends to infinity. So this is the meaning of Fx is equal to small o of Gx. So here is exactly the same thing you have. That means variance of X upon E square X will tends to 0. Thus what we can say, is probability of x is less than or equal to 0 goes to 0 if the variance of x is equal to small o of square x. If we have this situation, then we can say that the probability of x is less than 0 is goes to 0, and this is known as second moment. This will prove the second moment method, and there is a corollary of this result is also there, which is also very short, which says that let x be a random variable with the expectation of x is greater than 0, and if the e of x square is less than or equal to e square x into 1 plus order 1 small o of 1, then x is at most surely greater than 0. So the proof for this one is just simple by the previous result which we have discussed. Here we have e of x square is less than or equal to e square x into 1 plus small o1. So therefore this will gives me e of x square less than or equal to e square of x plus e square of x into small o of 1. So that will gives me e x square is less than or equal, sorry, minus e square x is less than or equal to e square x small o of 1. So that means this will gives me variance of x. This is nothing but the variance of x is less than or equal to e square of x big O of 1. So that means variance of x upon e square of x is less than or equal to small o of 1. And if you use the previous thing, that means probability of x is less than or equal to 0 is less than or equal to variance of x upon e square, which we already derived by Chebyshev inequality. So it says that this is less than or equal to small of 1. So therefore, the probability of x is greater than or equal to 0 is less than or equal to variance of x upon e square x, and that is equal to less than or equal to small of 1. But small of 1 is nothing but the tends to 0 as n tends to infinity. So that's why x is at most surely greater than 0, we can say. And the second moment argument are more difficult than the first moment argument when you're dealing with some item. For example, in the previous lecture, when we are calculating the variance of x, we have to calculate where x is the number of triangles. We need to see whether that number of triangles is independent or dependent. So actually, when we are dealing with e of xy is equal to e of x, e of y, then we require this x and y should be independent. Otherwise, we cannot write this equality. So the second moment argument is more difficult than the first moment argument whenever you are dealing with some situation. And however, if the in the example which we have occurred for the two triangles have the same common, if we have seen that if p is equal to d by n, then there are so few triangles as atmospherically no two triangles have same share the common edges, and the lack of statistical independence does not affect the answer. And in the next, or in this chapter, entire chapter which we are discussing, is regarding the phase transition of at most always a transition in the probability that item being present occur when the expectation of that transactions. We are discussing all such examples. So this is about the first moment method and the second moment method, and very important because whatever discussion we are doing afterwards, that is about the two degree of separation that is known as a diameter is 2. Maybe we are discussing about the disappearance of isolated vertices. Then it may have, we'll discuss regarding the Hamiltonian circuit, when the graph will have a Hamiltonian circuit, when the graph will have a giant component. All sort of things is required, these two arguments, that is first moment argument and the second moment argument. So that's why they are very important to discuss to see the further discussion. Okay, so I think so I should stop here for today. If you have any questions, you can ask.